It's a real pleasure to introduce Gang Tian from Peking University. We're all glad that you made it here in spite of your airplane problems. And he will talk about relative volume comparison along Ricci Flow.
Thank you. Thank you. First, I'd like to thank organizers for invitation. Especially I want to thank Claudio for arranging my trip. Especially for yesterday, I had this long delay and there are a lot of confusions. And anyway, it's my pleasure to be here. And it's actually, I have been in Brazil for a few times, but it's my first time in São Paulo, so it's good to be here. And today I will talk about joint work with Zhenrui Zhang. He's a professor, a young professor, young guy at Capital Normal University in Beijing. Okay. And so together with him, we have quite a few joint work in the last few years on the Ricci Flow. So today I want to talk about the relative volume comparison along the Ricci Flow. And I might looking at this such a nice audience and a nice auditorium, I realize maybe I made my transparent a little bit technical, but I try to explain well. Okay, so maybe I emphasize more on the things which are easier to understand. So less technical. So okay, so my talk will split into 3 parts. First, basically, I want to tell you what the result is. So then I will kind of summarize a bit of proof. So best want to emphasize points in the proof, and I try to do my best. So then I will give an application. That's actually the motivation to do this. One of the motivation to do this, but I believe this relative volume comparison is something one should. It's more important than application. Even if at the beginning, we try to prove this, solve this problem application, but in the end, we definitely the tool we developed is probably more important than others. So let M be a closed manifold dimension N. It's always like that in this talk. And we consider the Ricci flow, which was introduced by Richard Hamilton in 1982. So this is Ricci flow. And Ricci T stands for the Ricci curvature tensor of GT. Okay, GT is a family of metrics. And G0 is some given initial metric. Okay, so I mean it's quite common and in the conference for geometers you hear about the Ricci flow. So I won't go and spend too much time on that. Maybe I just mention a few. And many powerful analytical tools for Ricci flow were developed in the 90s. For example, maximum principle for tensors. So for that you can. And so in geometry, and one of the most important things is to control the curvature. So once you have this evolution equation for metrics, you can derive equation on the curvature, evolution equation on the curvature. Then you want to see what kind of property can be preserved along the curvature, along this curvature evolution equations. So this in this case you need to use maximum principle. Of course, the maximum principle has one here say Hamilton is probably what he did in the earliest time, but then there are also generalizations. For example, proving this curvature operator has sufficient nice properties was a work of Balmer and Wilking in maybe a few years ago. So also have a differential hierarchy inequality that's by Hamilton. So and and the derivative estimate of curvature. Here I only give a few examples. I didn't mean to list all of the analytical tools. Of course, and if you want to do that, you can give an expository talk on that, and that's probably take a whole 1 hour. But today I want to mention things is related to our talk is this Perelman's famous result called the long-collapsing estimate, which is a breakthrough in the study of Ricci Flow. So that was done in his famous preprint in 2002. So what is this non-collapsing things? Maybe first I'll state the result. So it's not a little bit long. So I will, in a moment, I draw a picture to illustrate what this means. So basically, Perelman has actually 2 versions of non-collapsed results. Okay, and one is using entropy actually, but that one is not kind of uniform. Here I state another version, which is in some sense is weaker, but is more uniform. It's uniform in the sense. Okay, so let's look at it. So for any constant a and the dimension n, okay, there's a kappa depends only on these 2 constants with the following property. If GT is a Ricci flow in this time interval, okay, and on this given manifold n dimensional, satisfying the following. So this is so on certain region, the curvature is bounded. Okay, so this is so here by this I mean the ball of a radius r0 and with center x0, and this is a ball, geodesic ball with respect to this metric g0. Is that the initial metric? So this is kind of like you can think is a parabolic ball, but it's a fixed sized. For Ricci flow, there are 2 kinds of parabolic neighborhood. This is a fixed parabolic neighborhood. So assume this. Okay. So maybe I draw a picture here. So if you think, so this is time, and this is a space. Okay. So this says in x0 here, and if you look at the time interval from to r0 square, okay. So this region take this is so this is like a b g0 of x0 r0. Look at this interval. So you then look at this parabolic range. Okay. So the first condition is curvature is bounded on this shadowed region, okay, on this parabolic region. So then the second condition is this non-collapsing condition, namely you want this volume. So this is the first one. This curvature is bounded. And this R0 minus 2 is all make it scaling invariant. And the second, this is the first condition. And the second condition is you want this volume of B G0 of X0 R0 of R0 to N equal to A inverse. Okay? Again, the constant is made of this, to be simple. You can put some other constant, then this kappa may depend on this constant too. Okay? So then you look at the conclusion. So you look at this at time tr0. So at this time now, so you look at this ball for this is x0. You look at the ball for much bigger radius. So this is a r0. Okay, so this is how that. So then in this you might have a region of this is x. Okay, so it's a region is measured at by gr0. So this is b gr0 square and x of r. Say r is less equal to r0. Say, okay, so So then, so you look at this non-collapsing thing says you want to look at the volume of this. Okay, collapsing means the volume of this is getting small. Okay, getting small. So this third condition is say if you assume this, look at this ball. Okay, and look at this ball of like this. And again, you look at a little bit of parabolic things, but you back a little bit. So I look at this way. Okay. So then the curvature here is Rn is less equal to R minus 2 under this ball of and across the interval, which is you back a little bit. Okay, you look at this. Okay, so then if on this if this condition satisfies, then you have this is conclusion. So then the volume of this ball cannot be too small. Okay, cannot be too small. So that's non-collapsing things. So this is even though this is stated in look at it's quite a long statement. Actually, in Paramount's paper, he stated shorter, but he took one part of that as a definition. So then you add up, it's exactly like this. Okay, nothing. So this theorem was proved by Paramount by using a monotonicity of reduced volume he introduced. Okay, I want to go into that, but later I will talk about entropy. So that's give you a better proof. So and it plays a crucial role in the proof towards the Poincaré conjecture. It was his proof for Poincaré conjecture, and what's used that is used to rule out the possibility of developing finite-time singularities along the surface of a positive genus. Okay, so this is very important. If you allow the Ricci flow to do a surgery along the surface of high genus, then there's no possibility of doing topological applications, because any three manifold you can produce any three manifold by making a surgery along the tori. Okay, so this is very important. The more precise, what he did is he basically has the so-called cigar solution. Okay, the cigar solution it's topology is like a cylinder, but near the infinity is not like a cylinder. So then you cross the cigar solution with S1. So the boundary at the infinity, I mean the cross section near the infinity is a torus. It's torus. You need to rule that out. Actually, the Hamilton did try it once in the 90s, and he called it little loop lemma. But then later I found that there's a gap in his proof, and I'm not sure that his proof still is fixed or not yet. But anyway, the Paramount comes in with these previous things to rule that out, because all these curvature conditions can be verified in that case, and then the only thing you cannot verify is the volume collapse. Okay, so that this cigar solution cross S1 cannot be as a model of a finite-time singularity in the three-dimensional Ricci flow. So this is a very crucial step in the topological application, even though it's you look at the previous case, it's very much like an analytical statement, and there are quite a few assumptions. Okay, but it's important. Okay, so assumption 2, namely this second assumption, this I actually should say assumptions. What assumption 2 here means this assumption. Okay, this assumption. So maybe I remind you. So that means this assumption, this 2 is here. The 3 is the conclusion. The 2 is this assumption. The assumption can be weakened to this. So this is weakened as a scalar curvature at R0. The time R0 is bounded from above. So instead of assuming this curvature condition on this whole parabolic neighborhood. So you only need to assume this scalar curvature condition on this geodesic ball on the given time. Okay, this is a much weaker assumption, and you can still get same conclusions. You get same conclusions. Okay, so that was done actually, first proved by Zhang Qi in his book. Okay, but it was probably in the book it was not quite noticed by all the people. So then later on was also given by Bing Wang, more recently. But actually it's already in the Zhang Qi's book. Okay, so such an improvement of Paramount is a non-collapsing estimate is very useful. Require new ideas in its proof. Its proof. Later on I'll probably mention a little bit. So it's useful. For example, Bing Wang used this to bound the diameter of a space and along the Ricci flow in the non-collapsing case. Okay, so what is our theorem? So a few months, a half year ago, or the early of this year, we proved the following things. So for any n and a, that's same as Paramount case, and there's a kappa such that the following holds. Again, let GT to be in this interval to be a solution of a Ricci flow on this n-dimensional manifold. So assumption at the beginning is exactly the same. So, but however, instead of a curvature, we assume a Ricci curvature. Okay, and this probably is not a very difficult step. Okay, and so assume the assumption 5 is we instead of assuming sectional curvature, assume a Ricci curvature. That's a bit of weakening condition. Weakened condition. So then we also drop this condition. That's crucial. We don't assume initial metric has a volume. So we don't assume this. So this we drop out. Okay. So want does not want our estimate depends on this initial volume things. Okay. So and then the third next assumption basically is we only have two condition now. And the next condition is still on this ball of these things on this ball. It's same as in the Zhang Qi and the Bing Wang case. So it's assume this curvature is scalar curvature is bounded from ball on this side. On this side. Okay. So then we have a non-collapsing. Not non-collapsing. Then we can compare the volume ratio of this geodesic ball at time R0 square with volume ratio, initial volume ratio, and this is big equal to that. Okay, so instead we make this assumption, we just put this in the conclusion. So in a sense, we get a more uniform estimate, which does not depend on a volume ratio at the beginning, initially. Okay, and so this is our main theorem. So theorem first is a generalized Paramount's non-collapsing theorem is clearly we generalize that, right? So we actually weaken the condition in several things, and this can be also regarded as a generalization of Bishop volume, Gromov volume comparison. So let's recall that if MG is a remaining manifold with Ricci non-negative, then for any these two radius, and the volume ratio of a smaller ball is bigger equal to volume ratio of a bigger ball. Okay. Of course, if you assume instead of assuming Ricci curvature bounded from below by 0, if you bounded from below by some constant, then you might have a constant here. Okay. So anyway, so in a space. In the space of with a Ricci curvature bounded from below, the volume ratio is somehow kind of controlled. So this is called a relative volume comparison. Now, certainly, relative volume comparison has played a crucial role in the study of Riemannian manifolds. For example, it can be used to prove the Gromov Hausdorff convergence of a space with Ricci curvature bounded from below, okay? Or say it's a point space. And also it plays a role in the Cheeger coating theory because that makes sure from a volume cone to a metric cone, okay? So in the Ricci flow case, we also hope to have that because Ricci flow, in a sense, at least we think, okay, but that's not quite. Is we think Ricci flow is kind of like, if you look at the Ricci flow as a space-time metric, which is degenerated, and it's like the Ricci curvature equation is regarded as a Ricci flat conditions. Okay, but however, the proof is much more involved than this volume, Bishop-Gromov volume comparison, which is come from a kind of Laplacian comparisons. Okay, so also it's as you will see, I will give an application later. So to my understanding is this Paramount's non-collapsing theorem is more like is very useful in studying finite time singularity because it has assumption on the initial metric. If you just study finite time singularities, it's okay to make assumptions on the initial metrics. But if you want to study singularities at infinity, it's not possible to do that. Okay, so it's because you cannot quite assume initial metric has some volume conditions. So this relative volume comparison theorem should be able to study this comparison, study singularities at infinity. For example, as application I will give to you is to prove a Gromov-Hausdorff convergence of Ricci flow at time infinity. Even though I did application in the so-called Keller-Ricci flow case, but it should be also applied to even three-manifold case and so on. Okay, so it should have more applications, so let me next I say a bit about the proof, and the proof used the localized version of entropy instead of reduced volume as Paramount did. And the crucial difference, as I already mentioned, between Paramount's theorem and ours is that the initial metric may collapse. Okay, so this causes substantial difficulty. So actually our proof is more involved. I will tell you. I won't tell you the detailed proof, but I tell you where some key points. Okay, and it took us a long time to do that. Okay, so I will show some ideas in the proof. So first, let's recall Paramount W functional. So this is Paramount W functional. So there depends on G, and F is a function, G is a metric, and tau is a parameter. Okay, so like this. So if you substitute F by U, okay, like this, you can rewrite this as follows. So this is essentially like a logarithmic Sobolev inequality, okay, in the form of functionals. Okay, so then we can study a local entropy. So I should say local entropy already used in this Zhang Qi and Bing Wang's work. Okay, so but we need to use it in a somehow different way. Okay, so using a local entropy was not our. We didn't do it first. Okay, so we can define local entropy, and so that's easy. We just take infimo of all the functions U, but with U vanishes on the boundary. Okay, so if omega is a whole M, then it has no boundary. Of course, they should just get Paramount's original entropy. So that's a local against Paramount's entropy. Okay, and but there's a difference. The difference is Paramount's original entropy because there's no boundary term, which is monotonic along the Ricci flow, as Paramount already proved. Okay. However, in general, the local entropy is non-monotonic. This causes new difficulty. The boundary contribute things, and it makes it not monotonic. Okay. At least not monotonic in a way you can easily see the result. Okay. So local entropy closely related to local volume ratio. That's what we noticed. And this also contributes to our assumption. For example, Ricci curvature assumption we used, and instead of sectional curvature, because we noticed some of these conditions between local entropy and volume ratios. The first is if a Ricci curvature bounded from below on the ball, and then this is you have this estimate. You have this estimate, okay? And namely the logarithm volume ratio at this time r square is bounded by this. Okay, so and also if a scalar curvature bounded from above, then we can also have this. No, bounded from below, no volume ratio in terms of entropy. But since it's not great, you have to take a kind of supreme or infimum in the time interval, among the time interval. It's not like exactly at that time, okay? But then life becomes simpler. So then what we can do is we may assume this GT, so to be simpler, so let's make R0 to be 1, okay? Otherwise you do in the scaling way, so in the scaling invariant way. So that A bigger equal to 1, so that's basically in our theorem you need to do here, okay? So let V to be a solution of the conjugate heat equation of Ricci flow. Okay, R is a scalar curvature, and you solve the backward equation as so. U1 is V1 is UA squared. So UA, what is UA? UA is the minimizer of this entropy at the time 1. At the time 1 with parameter tau here. Okay, for some tau fixed. Okay, so in the application you need to choose tau, which are probably not going to that. So then this you have this entropy, okay, estimate. So this is like monotonicity. So you play around the Paramount's monotonicity formula, but this time because of boundary, you will have something actual. Okay. So basically, this way we are doing here is a way of proving monotonicity in the Paramount's work. But however, in our cases, because of boundary things, you have some actual terms. Okay, and these actual terms comes out like this. Okay, so of course V is a positive, but you need to bound things. You need to bound this integral from below, or you bound this whole thing from above. That means this integral from below. We know in many cases bound things from below, you need some substantial work. Okay, so from here you can instead of, because these entropy things, if you look at a smaller domain, this may be plotted here. You just look at this, and this is at time 1. So that means at here on the ball of this size, on the ball on the ball of this size, A is R0. R0 is 1. Is this time is A. Okay, on this big ball. Okay, and so then so local entropy is minimizing among the functions vanishing on the boundary. If you look at smaller region, of course you have a few functions, so local entropy increases, right? So that's a simple fact. So then if you look at the region here, namely look at this smaller ball here, in this big ball, of course local entropy goes up. So that's why so this is simply a corollary, a consequence of a previous one. Okay, so okay. So if a Ricci curvature, if you have this assumption on a Ricci curvature, which we assumed in the theorem, so this time we actually only need a low bound of Ricci curvature and upper bound scalar curvature on this. So namely on this region, you assume Ricci curvature bounded from below, And here you assume scalar curvature bounded from above. Okay, and so then you apply these previous things. You need to play around a bit. Okay, and apply the previous things. This entropy relation between entropy and volume ratios, and then you can get these things inequality here. Okay, so some constant I don't care. So again, I need to bound these things. I need to bound this. So this should be R should be 1 here. Okay, it's R0. So I need to bound this from above. So it's the most technical part of our proof of volume comparison is to bound this from below, bound this integral from below. Okay, so how do we do that? Okay, how do we do that? So we need a new, to do that, we need a new estimate on the following heat kernels. So we look at the heat kernel to a conjugate heat equation which satisfies this. So in one variable, you look at it's like a backward heat flow, but this is a conjugate to a Ricci flow. And then the forward, you have this just standard heat kernel. Of course, it's not quite standard. We still have this Laplacian depends on metric, depends on time here, and Laplace depends on time here. So this is a backward heat equation, but twisted and shifted by this scalar curvature, and this is a flow. Okay, so this this heat kernel, I mean this equation was studied also by Paramount, but here we use a different. For different purpose. Okay, so here this is this just delta functions. Okay, so then what we need is to bound this heat kernel. So because solution now has this this is easy. Okay, the solution of this V, which is given by this backward equation, you can have this integral expression. Okay, so then in order to bound this integral of V from below, we only need to give a low bound of a conjugate heat kernel, namely these things here. So large part of our proof is devoted to bound no bound of this. Okay, so here is what we proved. So there is a T0 of between this some constant, forget it, so such that A bigger to 1, and you can bound this heat kernel from below by this, okay, and for this region. So once you bound this, and then you look at some V, because you can say V has some point has a low bound, and then you use the low bound of this, try to get the required no bound of integral. Okay, so I should say, so this heat kernel estimate is not because we have results on the no bound of heat kernels. For example, Chen-Yao estimate, Qige-Yao estimate. Okay, they are just for standard heat kernel. Namely, the metric is fixed, and when the curvature bounded from below. Say Ricci curvature bounded from below, or even in some cases curvature bounded from below. But here we consider different kernel. And this original argument actually do not come easily. We need to actually have new arguments. Okay, the proof is quite involved. So I want to go into that. Actually, I should also say this part of proof. Mostly, actually, was my young collaborator, made more contribution than I did in this part. Okay, so technically he did more. So anyway, in short, this Chen-Yao and this previous argument cannot apply to here. You have to develop certain new estimates. Okay. So once you do this, as I said, you can using a certain low bound of V at one point, and then to get this and this integral bound. Okay. So now we give application of our relative volume comparison theorem. As I said at the beginning, this is actually my our original purpose, try to prove this. But and then we realize there's you need to have some of this relative volume comparison. Okay, so let me give you some background. So let this time let X or is be a compact Kähler manifold is just M, same as M before. The complex dimension M. So N is twice of M here. So actually I maybe just should use M instead, but previous M now become X, and N is just 2M. Okay, so I consider Kähler-Ricci flow, and so it's in a complex coordinates. I dropped that's one. So G is represented by positive Hermitian matrix like this, and so this is so we usually denote this matrix by its Kähler form. So it's like this, okay, and the Ricci flow rates up to scaling is like this. Okay, so I dropped the 2 because you can reparameterize time to get rid of 2. Okay, so I for the Kähler-Ricci flow case is a bit easier to convenient to write in this way instead of put 2 there. Okay, so it's actually just a Ricci flow, but you reshoot the Kähler matrix, and it's automatically preserve that condition. Okay. And the Ricci curvature is again is a form of that. So in this case, we have a very nice existence theorem, which says for any initial metric omega 0, and Kähler-Ricci flow exists up to this time. Okay, so first C1 is a first Chern class of a manifold. So C1 is a first Chern class. It's more strict as this first Chern class. The first Chern class of a is actually represented by Ricci curvature. Okay, so this is in some sense why I somehow spend not time on Kähler-Ricci flow, or you can actually do things on a 3-dimensional flow, because in this case you have a very nice sharp local existence theorem. So this local existence theorem is given by some topological, some cohomological conditions. Okay, so in particular, if so-called this determinant line bundle cotangent determinant of cotangent bundle is NF, so in some sense this means first Chern class is, so this NF is equivalent to, or is almost equivalent to, say, it's a negative first Chern class is positive. So it's more like algebraic condition. In some algebraic sense, this is satisfied. Okay, and this is stronger than that. This is stronger than that. Okay, in general. So in particular, in the case, this is and has a global solution, because if my C10 is non-negative, then this is always positive for all the time t. So then this capital T is infinite. So you have a solution for all the time. Okay, so we assume that. Okay, let's assume that. Okay, so if you don't assume that, you need to study finite time singularity, which is there is a program called analytical minimum model program. Basically, so there are 2 steps. One step is you study finite time singularities. So finite time singularity exactly means we need to eliminate algebraic subvarieties, or eliminate the parts of a manifold such that this condition, this is positive. This is negative. Okay, so basically, the finite time singularity basically you want to do is you want to eliminate something so that and the positive part of a function class. Okay, so that this after finite man surgeries, this is satisfied. There is a lot of papers on that, but today I won't go into that because today with application I want to study singularity at time infinity. Okay, so there are a few cases. So if you assume this, there's no finite time singularities, and so then you just study the limit. So you study a problem when t goes to infinity. What is the limit? What is the limit? Okay, so there are a few cases. The first case, when the quadratic dimension, so-called quadratic dimension is kappa equal to 0. That's first. Don't worry about this condition. So this case is just say x is Calabi-Yau. Now Carl proved in 1986, a long time ago. He actually, in his thesis, he used the Keller-Ricci Flow to give a alternative proof for Calabi-Yau theorem. So Keller-Ricci Flow converges to a unique Keller-Ricci flat metric. Okay, that's it. So when the kappa is equal to n, so it's called x equal of a general type. So this condition means is in the sense if we do a differential geometrically, that means the non-collapsing condition. It's non-collapsing. Namely, this in this case of C1, this C1x minus n is positive. Okay, so this is a second case general. So this is equivalent to kappa equal to n. Okay. So this case, and we've considered normalized Ricci flow. So we rescaled the time, reparameterized time, and scaled the metric. Okay. So what we do is basically in the previous Keller-Ricci flow, you get solution omega, and you multiply omega by my t to minus 1. Then you will get a solution of this flow. Okay, and this is the Keller class goes this way. Okay, it's a solution. So here I mean the Keller class. It means the cohomology class represented by these forms is given by this. Okay, so then you can see as t goes to infinity, positive infinity. So this initial metric goes to 0. The contribution initial metric goes to 0, and then the Keller class goes to Chen class, first Chen class, minus first Chen class. Okay, so indeed we have quite a few results. The first by Suji in the 89, and later on by myself and Zhang Zhou. We try to clarify some argument in the Suji's proof. It's omega t converges to a unique Keller-Einstein current on this in this class, and that in this class means its cohomology class is same as this, and the convergence is smooth on the ample locus. So, or you can say convergence smooth outside the suborbites. Okay, so it's basically convergence is smooth on the part where this is positive. Is positive. Okay, but this convergence we did is only by solving a complex Monod-Champy equations. It's more like complex limits. So you study how the Keller potential things, and this convergence does not tell you much. Actually, tells very little on the singular locus. So maybe I explain a little bit. So I need to keep that part. So basically what you have here is this ample locus means this. So you look at x, okay, and you look at x0, which is look basically points, and I just write in the, okay, and called this way. How do I define this? So x 0, defined to be a point in the x where this kx is positive there. This is not quite a rigorous definition. Okay, you need to do it in the algebraic sense. Okay, in the open. So this is called and then you know this is open, and x minus x0. If you define this as S, this is a subvariety. Okay, the subvariety is this subvariety, and the kx is this is basically said the kx on the S is not positive anymore. Okay, so this this when I say smooth convergence, smooth, the omega t converge toward this omega Kähler-Einstein metric in a smooth topology on any and this E contained in this x0. Okay. So this convergence is proved by looking at the corresponding complex Monchampy equations and do a kind of estimate on the solutions. Okay, but this does not tell you much. Actually, tells you very little for the behavior of solutions along near the S. Okay, so for example, we don't know whether this omega t is converged to this in the Gromov-Hausdorff sense. So that's it's a global convergence. Okay, it's global convergence, including S containing S. So the first result was just 2-3 years ago was given by Zhang Song. He proved a Kähler-Einstein current Ke defining a metric on the canonical model. So this means so what he means basically what he proved is Zhang Song proved is a diameter of this x0, okay, omega Ke, so this time is a metric. This is finite. Okay, this is finite. Okay, this is Jones. And from here, as a corollary, with a little bit of arguments, you can prove the metric completion of omega Ke. You look at this. This is open. Okay, and look at the metric completion. Is X canonical, is a variety. Okay, it's a variety. It's called a canonical model of that. So I want to define. So this is a so-called canonical model. There's an algebraic way to construct this. Okay, so he proved this. You look at this metric completion is coincide with a canonical model defined by algebraic geometers. Okay, so in particular, this is compact. Okay, it's not trivial. Okay, as I said, the probability from the first part it does not even tell you this one has a finite diameter. Okay, so and then being one and. So also I mentioned one the dimension s equal to 3 together with Zhang in our previous work because we are always working on this for quite a while and converge globally to this, okay, in a Cheeger-Gromov sense. Okay, so that namely you also want this convergence to be smooth outside the flow converges outside this in the metric sense, okay. So this two-dimensional case also given by somebody else, and by Song and Song and Wankov, okay. So last year, Bing Wang he proved by using this improved Paramount's non-collapsing result. He proved a uniform diameter bound on the Ricci flow. So these previous things, So these two things together does not imply automatically the diameter of this is finite. Okay? It's uniform finite. This is a question. Okay? So that's what the Bing Wang proved. That's Bing Wang proof. You can get a uniform diameter bound. So then you can, from there, he didn't quite do that, but it should be possible, I think. And then the proof limit should be this canonical model constructed by Jiang Song. Okay, so that's also we conjectured in this analytic minimum model program. Okay, so this is about the non-collapsing case, because this case I said because of this positivity condition I already erased. This even at time infinity is non-collapsing. So if someone knows about this Paramount's proof geometrization conjecture, so maybe I make comparison here in order to because not all people know Kähler geometry that well. So in a three-dimensional case, so Thorsten's geometrization conjecture, you can have a refined version. Of course, Thorsten only concerned about topological aspect, but we can pretend we are not topologists. We just geometers and analysts. We just want to do what we can do. So what you can do is you start with the initial metric on the three manifold. You evolve along the Ricci flow. Of course, at the finite time singularity, you want to do a surgery, right? Of course, canonical surgery is still not known yet. It's the recent work of Bruce Kleiner and Richard Baumler proved this. You can do surgery which is continuously depends on the initial metric, but still it's not known is canonical. So actually, Kähler case we know a little bit more on this part. But suppose you can do that, and you have a finite time surgery, and you do finite many of them, as Baumler already proved. So then you have a long time existence for flow, okay, for Ricci flow on 3 dimensions. So you see what the limit is. So limit, you don't know you don't make any topological assumptions. So in the limit, presumably, of course, according to what we already know from a geometrization conjecture, is it should be along the split along the incompressible tori. You split to finite many pieces, and each piece carries a canonical geometry. It's one of 8 geometries, right? 1 or 8 geometries, and 3 of them are non-degenerate, so-called hyperbolic, Euclidean, and spherical. The spherical actually never appear, and the spherical actually only appear in finite time. So only basic 2 in the long-time limit is a flat metric and hyperbolic. So those 2 correspond to non-collapsing case. That's exactly what I said here. Okay, there are also 5 other kinds of geometry. They always degenerate geometry at infinity. So the Ricci flow, if you just look at the flow and you are strong enough, you analyze it, the flow collapse along the circles to a low-dimensional things. That's what I'm going to talk next. That's the counterpart of a 3-dimensional picture in the Kähler case. Okay. So of course, all this comes from a 2-dimensional things. And a 2-dimensional case is on the Riemann surface. You can use a Ricci flow to reprove a uniformization theorem. In the 2 dimension, you don't see that 5 kinds of geometry. That's called degenerate case. And you don't see these things on the next page, because 2-dimensional, by this time, everything is finished. Okay. But for when you go to high dimension, you either go to 3 dimension or go to Kähler in high dimensions. You got to run into this case, so-called Kodaira case. Kodaira dimension is between 0 and n. Okay, between 0 and n. Okay, so you see, n has to be at least 2 in order to have this case. All right, kappa is an integer. Okay, so let's see this case. So what is a typical situation for this case? So the typical situation of this case, very simple situation of this case is the following. So typical situation in this case, you look at one case is a simplest case, is a sigma of G cross with T2. Okay, this is G is genus of big equal 2. Okay, so this time on the flow, in the limit, you take the Ricci flow. This time, it should converge to a metric on some metric on the infinity on the sigma infinity. So namely, you should collapsing these things, And the more complicated, more generally, you can look at a situation like this. You have a map from your manifold into some other manifold we call the X canonical. Okay, and this is m dimension, I said, and this is the kappa dimension, and the kappa is less equal to m. N should be m. Sorry, so I switch n and m. So, okay. Should be between this, okay, and the fibers such that the fibers, generic fibers, take Y here, is a Calabi-Yau for generic Y. This is almost every cases for these conditions. So and to prove for these things, and this condition is always have this picture, is called abundance conjecture. It's not solved yet. That's probably what's left open in birational algebraic geometry. Okay, the biggest problem one of the biggest problem in the birational algebraic geometry. But let's say we assume this. Okay, and there's also an analytic approach, but this, anyway, has not finished. So it's a typical case. This assumption here is like this situation, and suppose this is all the situation, though we don't quite know yet. Okay, so for example, if a fiber dimension, or that is m minus kappa, is 1, then this has to be tori, right? So if m minus kappa is 1, like m equal 2 case, then this has to be tori. That's only Calabi-Yau in the one-dimensional case. Okay. So I'm sorry, I have looked at the time. We got no clock here. Oh, sorry, I'm a little bit too slow. Let's do faster. So I have maybe a few minutes. I will start a bit later. So anyway, so in this case, it's prove the convergence of Ricci flow to this in the current sense. They also prove C0 convergence on the potential level. Okay, you write. If elliptic surface is C1 alpha, and later they prove the C1 alpha convergence on the potential for all the things. And more recently, Tosadi and Vankov, Yang improved the Feng and Zhang's estimate to show that there are a lot of Zhangs. So this Zhang is Zhangzhou, it's not that Zhang. In Chinese, there are probably 80 million Zhangs, okay. Show the metric omega t converge to this in the C0 topology. So actually they prove a convergence of topology, okay, on the metric level. So previously it's only on the potential level. So namely you locally write the metric DD bar functions and look at that potential functions. So when the generic fiber are tori, they actually proved. So basically they proved and generalized to a Keller case to prove the smooth convergence of this. And in particular, on the regular part, this Ricci curvature condition is satisfied. Okay, but you need to assume fibers are tori. You need to assume fiber tori. In high dimension, it's not always true. Okay, so let this. the metric completion of this. And probably this space maybe has an infinite diameter. Okay, it's not clear. No. So it was conjectured by myself and Jiang Song, that this should be converged in the Gromov-Hausdorff to a generalized Kähler-Einstein space. This. Okay. So this is not the generalized Kähler-Einstein. Is some canonical metric too. So it's like in a three-dimensional Thorsten case. There's this canonical geometry. So it turns out in this case we can also define a special this canonical geometry, which is not Kähler-Einstein. Okay. So it's known from and this collapse phi locally uniformly. So difficult how to control size of singular fibers. So relative volume comparison along the Ricci flow just overcomes this difficulty. So all this estimate we did so far is on the regular part. It's on the part. So on the part 1, the pi is a regular value. Okay. So on this part. So let me plot this way. So this is x0. All this nice convergence is on the part is pi inverse of a pi regular value of pi. So namely fiber is nice. Okay. So on this part, and you get all this, and all this estimate can be interpreted in terms of potential estimate in terms of complex Monge-Bay equations, though in some degeneration in the degenerate cases. So as a corollary, in the same paper we proved, is a compact Kähler manifold with on the codine dimension 1. I tell you why codine dimension 1 is needed. Suppose the Ricci flow satisfies this condition, and this is true if fibers are tori. Okay, that's proved by Feng and Zhang. So then these converge in the Gromov-Hausdorff topology to generalize Kähler-Einstein metrics. Okay, so this is so we have a global convergence. This is the first global convergence in a collapsing case. So to prove about we need these things on the thing. So that's why we use kappa equal to 1. This is one-dimensional, and this Zhang Ya-San proved the generalized Kähler-Einstein space is compact. Okay, so namely diameter is finite. So let me drop that. So then by using volume comparison, relatively we can further choose any base point. Okay, and the collapsing rate of a singular fiber is controlled by collapsing rate of a regular fiber. So I'll say follow. So I back to this picture. If you regard this case, so this is a part contained in the x0. Okay, and this part we can control everything basically. We can control everything and our assumptions. So this part is near the singular fibers. So we can bound the volume ratio of this in terms of volume ratio of. Sorry, we can bound the volume ratio of this in terms of volume ratio of. What do I say? Okay. One way or another. Anyway, so I want to confuse now. So you use a relative volume comparison. If this things does not collapse, okay, and near a singular fiber, you can find a ball for radius, and so that the volume ratio is not small as needed, as required by volume comparison. So then you can prove near the singular fibers, everything is also collapsed to a point in the limit, in the metric sense. Okay, so this is the last. So then we can get as that X to be a Kähler manifold. This if generic fibers are tori, then any Kähler Ricci flow on the X converging in the Gromov-Hausdorff sense to this generalized Kähler-Einstein metric space, and which has a finite diameter. Okay, the key point to prove a diameter finite, and in particular, this Kähler Ricci flow on a smooth minimum elliptic surface. That's a complex surface case, namely m equal 2 case, and this case, this condition is automatically true, and then it converges to this. Okay, so this is that last statement was conjectured by myself and Jiang Song in 2006 in our first paper on this analytical minimum model program. So the case of higher quadratic dimension is not clear yet. So there are two difficulties. One difficulty is about the diameter bound of a generalized Cannon-Einstein current. Another technical difficulty is about the Ricci curvature estimate and the Cannon-Ricci flow. So because in order to use a volume comparison, we need to know the Ricci curvature on this part is bounded. Okay, so now we only know that based on these other people's results is when the fibers are tori. But if a fibers in high dimension, the fibers here may not be tori. It's general Calabi-Yau could be K3 surface, for example. So in that case, how to bound the Ricci curvature? It should be true, but we don't know yet. Okay, and so these are two things left. It's more on the so should have a more refined estimate on the complex Monge-Champy equation in the degenerate cases. So anyway, thank you. Sorry for a little bit over time.
Thank you very much for your talk. Are there any questions?
So in the Bishop-Gromov case, the rigidity version has a few important consequences. Is there a rigidity version for your relative volume comparison and any meaningful geometric consequences?
That's a good question. So in the Bishop-Gromov case, because you have this sharp constant, and you can use this ODE to do that. And in this case, we don't get a sharp constant yet. It's probably very hard to get a sharp constant. This is related to this heat kernel estimate. How you get a heat kernel estimate and in the sharp way. So, I mean.
Any other questions?
Lars. Yes.
So is there any hope of doing similar things when non-compact?
I don't think here is compact is really. It's because you look at the statement, it's all like on a elastic ball, so it's not about the compactness. But in order to use this, you probably need in the non-compact case, you need to know that Ricci flow can solve up to some time, which was not entirely clear for our case.
Any other questions? Then we have a coffee break now and start again at 10:50. But let's first thank the speaker again.
Thank you.